Hey, what's up, guys? So today I want to introduce this Azuma inequalities and its proof. And this Azuma inequality is interesting because usually in the in the inequality of probability that you usually need to assume that every random variable are independent, but in this inequality that you don't need to do this. And I have collected some of inequalities that in my video list. So if you're interested, you can check it out. Okay, so let's start. Okay, so before we start, let's quickly recall that recall these Hofstad's inequalities. So I will quickly go through the proof of this inequality and to tell you why usually the independent is a trick. Okay, so the idea of Hofstad is that if you have a random variable, they're all independent. Then you also know that they are bounded by a part, bounded by some lower bound upper bound, and then you can ask probability of some of them are greater than or equal to t is bounded by exponential of minus 2t squared summation of bi minus ai I from 1 to n. Okay. There is also constraint that expectation of x is all zeros. Okay. So proving idea is that you just write this as a probability of exponential summation of lambda I and take the lambda. So there's a lambda here and the greater equals to exponential lambda t. Okay, so this is a Chernoff bounds idea. So once you prove this, then you can use the Markov. So this guy's Markov inequality. So you get expectation value of exponential lambda minus xi I divided by exponential lambda t. Okay, so now you can now this guy, right? This guy is exponential of something, so it's very happy that you can always write these guys into sum of the you can always write this guy into sum of the random variable. Okay, what's going on? Sorry, let me just. Okay, so that means that you can write your expectation value of exponential of lambda xi, right? So you get sum from 1 to n. This guy, right, can be expressed into this. Okay, so now you can use the independent. So this is a trick. Now you can use independent. Okay, so once you go through this, so then you can prove the results, right? Because you have this guy and you have this guy, so you can write as this guy. Okay. So this is just a quick reminder. If you want to see the rigorous proof, that you can check out my videos. So this part is that why you need independent. Right, so basically, if there are two variables independent, then basically you can write as two sums. Okay, so Azuma inequality that is interesting because in some special case that you don't need independent, but you can still get some results. Okay, so I will prove the Azuma inequalities with two versions, and their relation will just leave you to think. Okay, so Azuma's inequality. Okay, so we have version 1. But version 1 is that you have x1, x2, they're all independent variable. Sorry, not independent, so they are not necessarily independent. And let's suppose that all these xi are bounded by Li, so there are absolute value are bounded by Li. And then you assume that you also assume that there are any product of x, different x will give you 0. So it's xi1, xi2, of the xik are all zeros. Like I1 different from I2, different from I3, so they are all different. Then you can still have the inequality, which is really weird. Expectation value exponential of minus like 2t squared summation of Li squared. Okay, so yeah, this is like the Azuma inequality. Okay, so I just noticed that previous I used lambda, so let's use lambda. Okay, so you can see that looks almost the same as half this inequality, right? You can check out almost the same as this. Okay, so it has the same, basically it has a tail bound, right? Like some exponential lowering. Okay, so proof need to use like two lemma. So let me just first introduce. So lemma one, which is very simple. If you take the AI plus BI and you go from the I from any one of them is n of them, and you take the expectation value, right? So since every product of X will be zero, right? Whatever length of the product X, so this guy will just be this. Will just be you take out the AI and I from one to n. Okay. The second one is that let's consider f equals exponential ax, where a is just some real number, and you can the derivative still a exponential ax. The second derivative a squared exponential ax. Sorry, so this guy is greater than zero, so tell you that f is convex. Okay, so if you draw a picture, then let's say consider this is x and 1 and minus 1, and this point will be 1 exponential a. This point will be negative 1 exponential negative a. If you draw the curve looks the same, looks this, right? And then if you draw a line goes this. Okay, so this we need to use the black. This black line is greater or equal to the blue line. Okay, so now we translate into mathematical language. Okay, so first we just find a black line. So black line is very simple. You start from 1a, 1 exponential a, and then negative 1 exponential negative a. So you first calculate slope, right? So you can y equals to slope. Slope is just exponential a minus exponential negative a divided by 2, x plus 1, x equals to 1, then you get exponential a. So you have this. And so y is just cosine a plus sinh a and then x. Okay, so this tell you that when x between minus 1 and 1, we have cosine a plus sinh ax greater or equal to exponential ax. Okay, so this is our lemma 2. Okay, so now we have these two lemma that we are able to prove this Azuma's inequality. Proof. Okay, so let's do the same thing, right? So everything start from doing the same thing. Is that we need to consider the probability of xi, let's say greater than lambda. Okay, so this guy is also the same as probability of exponential of xi. Let's say I add some t here. So now I use t as a variable. Okay, so I can make out any t where t will be determined later. Okay, so now we have this. Then we can use the Markov. Okay, so this guy will be Markov, right? So we can use the Markov. So this is potential value of this potential value of exponential xi let's say divided by exponential value of lambda t. Oh, sorry, there's this. Okay, and all right. So what's the problem? What's the problem? Right, the problem is to bound this, right? Since remember the previous that in Hofstad's inequality that we can bound this, right? Because these are independent. Okay, but now we are not able to bound this. But remember that we have this powerful lemma, right? So we can write exponential t xi. We can just write this. I can still write as product of 1 from 1 to n and the exponential txi. So for each exponential txi, I can write as exponential txi divided by li and li, right? Because li are just some factor. But this will force the xi divided by li to be 1 or minus 1. So I can use this as x and the tli to be our a. Okay, and apply our lemma. Okay, so this will tell you that our exponential t of xi li is bounded by cosine a, right? So a is t li bounded by sinh a. So plus sinh x sinh a. So x is xi divided by li sinh t li. Okay, so our expectation value of exponential summation of t xi, I from 1 to n, will be bounded by expectation value of cosine TLI plus XI sinh TLI. Okay, so now by our lemma 1. So our lemma 1 tells you that wherever xi product expectation value of 0, so this guy is bounded by expectation value of cosine TLI. Oh, by the way, it should be product here. Yes, should be product here, right? But these products, let's say I from 1 to n, is still not give you any results, right? Because this guy will give you the product. So you don't need this. Okay, you don't need this, and then your results will be I from 1 to n cosine t. Okay, and the cosine TLI is less or equal to exponential of t squared li squared divided by 2. Okay, so this is simple that you can check by yourself. So this one is less or equal to exponential of t squared li squared divided by 2, and the summation I from 1 to n. Well, this is simple exercise. We just write this cosine as Taylor expansion. Okay, so right, so now we can bound this, right? And we have this. Okay, so now let's write down our results. So the probability of xi greater than lambda, summation I from 1 to n, less or equal to expectation of t, summation xi, I from 1 to n, divided by exponential lambda t, where these guys exponential less or equal to exponential t squared divided by 2, li squared, minus t lambda. Okay, so this is the standard quadratic form. Then you just simply choose. So I think up to now, I don't need to tell you how to do, right? So you just do a derivative on t and whatever. So it's a t equals to lambda li squared, I from 1 to n. Plug it in, will give you a result. Okay. Okay, so you can, if you plug in, then the final result you will get this that's equal to exponential minus t squared divided by 2 of summation, lambda squared, and li squared, I from 1 to n. Exponential of minus lambda squared divided by 2 times I from 1 to n li squared. Okay, so this is like Azuma inequality, like one kind of version that, so the proof idea is still the same, right? You try to find the expectation value of this guy, and you hope to give the bounds. But previously you're happy to do because they're independent, but now you're not independent. But if you assume that there's strange constraint, that you can still prove this. Okay, so this is like a first version of Azuma inequality, and there's a second version that involves the idea called Martingale. Okay, so hopefully my pronunciation is correct. Okay, and yeah, you can check out other video. You can check out other people's video if you want to know what the hell is Martingale. Okay, so let me just quickly say what the hell is Martingale. Basically, Martingale is basically let's say if one just tell you z0, z0, z1, z2 are Martingale up to zn satisfied. If you take the expectation value and of, let's say you fix like zm, so zi plus 1, and you ask if you fix the 0, z1, and up to zi. So let's say so this notation means that you take expectation value, but you prefix the previous condition expectation value. Okay, this guy will be zi. Okay, so this is called Martingale. Okay, and so the version of this second version of Azuma's inequality just tell you that if you have this Martingale sequence, and you also give you a constraint that there are at most L increment. So this idea is called L increment, means that zi minus one, right? Every step cannot bound it by themselves some ci. Okay, so like every step you difference as small ci, then the probability of Zn minus Z0 greater or equal to T is bounded by exponential negative T squared divided by 2 summation of Ci I from 1 to N squared. Okay, you can see this is almost the same. This is exactly the same as if you replace this to be lambda, you get exponential lambda squared divided by 2 to Li, 2 divided by 1 sum from I from 1 to N Li squared. But this guy we use a Ci. Okay, but I will not tell you that what's Martingale in previous. If you want to understand, you need to understand the idea called filtration, and I think it's not suitable for me to talk about this kind of thing in this video because it's so long. So so I will prove this version, but I will not tell you that why this version is the same as. Actually, you can prove. Actually, I think you can prove that this version, this second version, of Azuma inequalities is still uh can prove. You can prove both. Right? You can prove this is true, then previous true, this guy's true. Okay, so but the least proof is still simple. Okay, so let's prove. So this is like version 2. Okay, so version 2, you take probability of Zn minus Z0 greater or equal to T, then you still use a certain trick, right? So what else you can do, right? So you can still use a certain trick. So let me just skip some previous step, some stupid step. Let's quickly go through the results. So I from 1 to N, Z minus Z minus 1. Okay. So since they are not independent, right? So you cannot spread out. Okay. So the idea is that it looks like up to now you cannot do anything, right? If all the ZIR there's no other relations, but in this problem that we have this strange Martingale relation. So now you can use a very weird trick, right? Write one expectation value into two expectation values. So okay, so you can write this guy into expectation value of expectation value. Let me just so I will explain this, but need some time. So you can write f from 1 to n lambda zi minus 1 conditionally on z0, z1 up to zn minus 1. Okay, so this is like famous rule of the condition probability. Okay. So basically, you can write this expectation on condition on this, and then fix on this. So this guy's expectation value expectation value over this, and then in the middle one that you just take this. Okay. Okay. But the problem is that since if you fix this, right? If you fix this, then this probability is actually only will be a constant, right? Will be a constant that since you already condition on the previous z0 up to z minus 1. Okay, so that means you can write this guy into exponential lambda t and separate into these two expectation values. So let me just write down. So you get expectation value of I from 1 to n minus 1 exponential lambda zi minus 1. Right. So since you fix up to n minus 1, right? So fix previous n minus 1 constant and the expectation value of I from 1 from n minus 1. Sorry, it's not this is too fast. So I take out the first previous one, right? So there should be remaining guy. So okay, so remaining guy is this lambda zn minus 1, right? Because these guys still remain, right? The fix on z0 up to zn minus 1. Okay. So now we know that this guy is Martingale, right? So this guy is Martingale. So since it's Martingale, so we have expectation value of Zn minus Zn minus 1. Condition on Z0, Z1 up to Zn minus 1 are zeros. Okay. And you also notice there's bounded by Cn. Okay, so now up to here that you can use the Hofstad's inequality. Okay, so let me just write down. So yeah, maybe it's complicated. Let me just clean here. Okay, so let's start from the last inequality here. Okay, so we start from here. And so you can use the Hofstad's lemma on this part, right? Okay, so this part is basically bounded by okay, so let's write this equal to lambda t and the exponential lambda squared cn squared divided by 2, right? Because this guy is exponential lambda zn minus 1, and then we know that zn minus 1 is bounded by cn, right? So you can use Hofstad's lemma on this part, okay? Due to this Martingale, right? Because this guy is bounded by n minus 1, and then this guy is also n minus 1. Okay, so since it's Martingale, so your results will be this. So now everything you already deal with this term and this term, right? So the remaining is this exponential term. So you get exponential value of I from 1 to n minus 1, lambda zi minus zi minus 1. Maybe just let me just write this down. So your result is this. Okay. Okay. So this is your probability, right? Now you can keep going, right? You can keep using this idea and take out the second term, take out this. You can write this as the condition probabilities. Keep going. So your final results will be Zn minus Z0 greater or equal to T, less or equal to exponential of lambda squared Ci, right? So now you extract every term. So I from 1 to n divided by 2. And the final back exponential of 1, right? So minus lambda T. Okay, so now you just choose lambda as before. Okay, so as before means that you choose lambda to be t divided by summation of ci squared I from 1 to n. Okay, once you plug it in, then you get the results. You get your final results is probability of zn minus z0 greater or equal to t is the exponential negative t squared divided by 2 of I from 1 to n ci squared. Okay, so this is like this is the results. Oh, very difficult. I mean, this kind of proof is like suck. You need to do a lot of things. Okay, so this is like two versions of Azuma inequality. One is you don't tell about Martingale, and one is that you need Martingales. And two kind of proof. Okay, hope you guys like the channel. Subscribe to my video.